All right. So this is the last lecture series that we will be starting, and then Ben's and Rahul's will continue on to tomorrow. So I'm very happy to welcome and introduce Rahul Angulo. I've known him for several years now, I think since my postdoc days. So Rahul is one of the leading experts in the world right now on numerical simulations in the cosmological setting. And he's been responsible for not just code development, etc., but also pioneering new techniques and pushing our knowledge of how to simulate interesting systems out to the cutting edge. So I hope you will enjoy his talks and also see a flavor of this in the course to follow. Please.
Thank you very much. Yes, I'm very happy to be here. Thanks for the invitation. So my lecture is going to be about how we simulate the structure, formation, and evolution in the universe. So this is a picture showing the results of one of these large simulations, and where we can see all the filamentary pattern, and we are going to try to understand the first principles and the underlying equations behind the numerical simulations. That's going to be the first lecture. And then the second one, I'm going to review what type of flavors of different simulations we can do nowadays when we change the nature of dark matter or the nature of gravity. And in the third lecture, I'm going to try to give you a hint of and a flavor of what the current research in this topic is by telling you how we can improve upon these simulations, how we can use them for estimating cosmological parameters and other things. So I wanted to start with this picture. This is the Hubble Deep Field, that's one of the deepest images ever taken by us, by the humanity. That shows a lot of different galaxies to very early stages of the universe. And we can see when we see this picture, and also when we see maps of the distribution of these galaxies, that the universe is very rich and complex. So we have galaxies of all different types and colors, sizes. Some are red, very passive, other blue, forming a lot of stars. Some of them could be as small as a few kiloparsecs, others could be up to hundreds of kiloparsecs. And then when you look at them on large scales, you see, as I was also showing you in the previous image, all these rich network filamentary structures that are huge voids that expand hundreds, even hundreds of megaparsecs in diameter, have huge clusters with hundreds of galaxies in them, and also filaments and other structures. So the basic question we want to try to answer is, can we explain this diversity in the universe? Can we use the laws of physics to understand why the universe is like that and not different? And if so, if we are able to understand why the universe is like that, can we use that fact to understand about fundamental physics, about the main ingredients of the universe, about the laws of physics, about how the universe came about and what its fate is? So this is in principle a solvable problem. It's if you want, an initial value problem that we know what the initial fluctuations in the density field were by taking pictures of the cosmic microwave background. And we know the physics that is at play afterwards, right? We know that gravity and baryonic physics, right? But despite of this being a deterministic problem, it's very hard to solve, right? So it's very hard because despite in the initial conditions, at very early time, the fluctuations were nearly perfectly Gaussian and the fields were well described by linear theory. We can solve this and understand this pretty well. Gravity very quickly will couple different scales and create all these nonlinear structures. We will see that the density fields and velocity fields become highly non-Gaussian. They become non-local. The process by which you form these knots does not depend on the local properties, but also on the tidal field and the large-scale environment. There might even be some stochasticity at play. And even if we predict what the nonlinear state of mass is in the universe today, we still need to account for baryonic physics. We know that gravity is not the only force in the universe, but there are also hydrodynamic forces and other processes like star formation and feedback from supermassive black holes and so on. So that makes the problem even harder. And so we observe typically galaxies that they're also a biased tracer of the underlying field. They trace the underlying velocity field also in a non-trivial manner. And of course, when we observe the universe, there are also observational effects, right? We select certain type of galaxies, there are completeness issues, and so on. Right. So in principle, this is a problem that can be done, despite all the complexity, through numerical experimentation, through numerical simulations of these underlying equations and initial conditions. Right, so we can take the universe as we think it was 300,000 years after the Big Bang, put the equations and these initial conditions in a supercomputer, and arrive to this state. Right? This way of trying to understand about the universe is sometimes called the third leg of science, right? Where it's not really experiment, it's not really analytic theory, but it's numerical experimentation. It's experimentation of a set of equations and physics laws. Right? So now for a given set of components and a model for the evolution, we can now predict what the low redshift universe should look like. And this is the evolution of the universe as predicted by one of the state-of-the-art simulations, the Eagle runs. We see that the universe initially was very homogeneous. There were these tiny fluctuations that because of gravity start growing, and you see that high redshift, they start forming all these patterns. If we go to the gas, to the baryons, now we see that they are condensed at the center of these large clumps. They're called dark matter halos. And then you see all these other clumps of gas that will start cool and start merging. And these are the places where galaxies form. Right? At the center, the galaxy, because the gas conserves angular momentum, starts settling into a disk. Stars form. Now this is showing you the distribution of stars. But the process that now we arrive to redshift 1, which is close to the peak of star formation, you still can have more gas being accreted. Now you start, these galaxies start look like the galaxies that are in the real universe, right? But they are very, very dynamic, right, in these simulations. So by lower redshifts, the mergers have stopped, and the galaxies have settled into a nice disk, and well, we can see now the distribution of stars in this nice spiral galaxy. Right? So now we zoom out and we switch again to the dark matter, and we can see how now this pattern is very similar to the pictures that we see today. So this is the state of the art of our knowledge about how structures form in the universe, and it has been largely thanks to the numerical simulation of the underlying equation and physical processes. So on a more quantitative level, we can explain the universe very, very well. So here is predictions. First, these are two measurements of the distribution of galaxies, as seen by two galaxy redshift surveys, the 2DF and the Sloan. And the bottom, these reddish pies, are the predictions from the Millennium simulation and a galaxy formation model. So you can see that the overall structure of the universe can be reproduced and understood quite well. On a more quantitative level, we can take these galaxies and see, for instance, what is the amount of dark matter that there is around. Right? So this can be measured through gravitational lensing, and this plot is showing you the measurement of this amount of mass as a function of distance from galaxies of different types. Right? So if we take, for instance, very massive galaxies, the red line, the black line, the measurements are the symbols, and the predictions from this particular simulation are the dashed lines. You see that the agreement is very, very, very good. And we do this for different type of galaxies, from these to very massive, above 10 to the 11 solar masses. And we go down, passing Milky Way type galaxies and a little bit below. And you see that for all of them, we are predicting correctly the correlation between the amount of stars in galaxies and the dark matter. So it's another, I think, a remarkable success of numerical simulations. Right, so nowadays, these numerical simulations can only predict one particular observable, but they are used on many, many different areas of modern cosmology. So on one hand, we can build universes like I was showing you before to create virtual universes. We can use them to test, for instance, analytic treatments of large structures. I believe you had lectures about perturbation theory, so you can do perturbation theory and compare with the results of these numerical simulations. We can play and experiment on these equations by changing the different components and see the impact, for instance, of massive neutrinos. We can run our simulations with and without neutrinos or changing the masses, and we can see what are the observable consequences of such a modification. We can use them to understand errors, and like as you heard in the previous talk, it's very important to quantify the uncertainty associated to your measurements. In the universe, we cannot repeat the experiment many times, right? We have only one universe. So the most reliable way of associating uncertainty to our measurements is by numerical simulation. So you simulate it many, many times, and then you can see the distribution of number of galaxies on a particular patch of the sky. And then you can even push this further and then try to do this varying systematically all, the cosmological parameters and try to see which combination of the abundance of dark matter and the spectral index would best reproduce observations. So these are, this was a way for me to give you motivation for why the numerical simulations are important and so crucial in modern cosmology. So now in this first lecture, well, these are the topics for my 3 lectures. In the first one, we're going to focus on the basic methods and algorithms that we need to understand and develop so we can run this type of numerical simulations. As I was telling you earlier, we need 3 ingredients for our numerical simulations. The first one are components, the components of the universe, then the initial conditions and the physics. Right? So in the components, there are many the species that we know exist, and they should be incorporated in their simulations. We know dark matter, dark energy, neutrinos. The universe it's not necessarily flat, so there might be an amount of curvature and also radiation. The initial conditions are determined by the shape and amplitude of the primordial fluctuations that we can constrain by CMB. And there could be also primordial non-Gaussianity that would propagate through these numerical simulations. And then the physics, we know that general relativity is very important to explain the evolution of the universe. Also gravity, itself, Newtonian gravity is important to describe interaction on smaller scales. And also it's important to account the process related to the formation of galaxies. So putting all this together, so we can predict the structure in the universe. Right, so for the sake of this lecture, we're going to make some simplifying assumptions. So these are, so if we are focused on, or we're interested in relatively large scales, above 100 kiloparsecs or so, we can make some simplifying assumptions. For instance, in the ingredients, we can treat all the different species as a single gravitating component. We can assume that there is a cosmological constant. We can assume that dark energy is a cosmological constant, so only affects the background. We can assume Gaussian initial fields and use GR only to tell us what the overall expansion of the universe is. So this set of 3 assumptions, well, maybe not this quite, but certainly these 2, is what usually lead to what is called dark matter-only simulations, right? Or more precisely, they should be gravity-only simulations. And this is the case we are going to focus on now. Later in the other lecture, I'm going to try to relax these assumptions and see how the results change. Right, so why this is a good approximation? We have evidence for that from a different set of observables. The first one is that dark matter is the dominant component in the universe, the dominant gravitating component in the universe. Several observations tells us that they are roughly 80% of the amount of mass in the universe. And dark matter should interact only gravitationally. Yeah, it's also consistent from the observations that dark matter is cold, meaning that the thermal velocity of the dark matter is much smaller than the coherent motions of the dark matter. And some of the best constraints come from observations of the Lyman alpha forest, which is if you take very high redshift quasars and you look at the spectra, you can detect all the intervening gas clouds from all the way from high redshift to low redshift. And by quantifying the statistics of this absorption, tells us about, more or less directly, how cold dark matter is. I'm going to come back to this later. Also, so far, despite many efforts, there's no detections of departures from Einstein's gravity, nor from a cosmological constant. So, and also there are many experiments, for instance, from Fermi, from the Fermi satellites, or the observations of the bullet clusters that indicate that, or to our best knowledge, dark matter has zero cross-section with photons, and also does not have also with itself, right? So you can be considered as a collisionless fluid. Right, so now we had these relatively complex problems with many ingredients and many interactions, and now we simplified it to the evolution of initially smooth, called classical, so we're neglecting all quantum effects, and collisionless fluid that evolves under self-gravity, right? So we just need to take this cold fluid and evolve it, right? So in principle, this is relatively simple. You just solve the Hamiltonian equations of motions and for many, many particles, and that is a solution for how for the evolution of the universe itself, right? So how do we do this, right? So let's start considering a group of particles. These are going to be our dark matter particles in phase space. So phase space means position, velocity. So we have a group of dark matter particles here on a du dx volume. This is a phase space volume. That is determined by a distribution function f. Right? So it's going to tell us how many particles we have here. Right? And now imagine that these particles are evolving. Now you can find them at a different location. Right? So now the initial number of particles is going to be the integral of the distribution function f over the phase space volume. And now it's the same. Right? But now x, you can imagine, is x plus delta x, and velocity is u plus delta u, and at time t plus delta t. Right? So now you can compare these two numbers, and they should differ only up to collisions. Right? So if you might have particles that might be entering, or there will be particles colliding here and kicking particles away. So that is the only term that should remain if you take the difference between these two numbers. So now you can expand this to do a Taylor expansion to first order, and then you end up with this expression. So it's the f. So it's f evaluated at x, u, and t, plus derivatives of f with respect to time, position, and velocity. Right? And then we have this collision term. So now you can use these previous equations, right? And now you end up with this expression that tells you how the evolution of phase space should be, right? You can furthermore use the Newton's equations telling that the velocity is the time derivative of the position, and the velocity, the time derivative of the velocity is given by the force. So if you put all this together, what you end up is with the famous Laplace of Poisson equation, right? So they also called the collisionless Boltzmann equation. Okay, actually, that's just telling you this conservation of phase space along the characteristics of the system. And it's supplemented by the Poisson equation that's just telling you that the total force is going to be exerted by the mass distribution, which in this case is the integral of the distribution function over velocity. Right, so this is not a formal derivation of this equation, but gives you a hint of what it's capturing. Right? So there are some consequences of this equation that tells you that this distribution function has to be continuous everywhere in space. It cannot have holes. It cannot also intersect with each other. One part of the distribution function cannot cross other parts. And you can imagine now that dark matter, because being cold, you have let's start with this simpler case. It's a 2 + 1 dimensions, 2 positions, and 1 velocity. And the dark matter occupies as a submanifold within this larger space, because at a given position, x and y, you can only have one velocity. That is what means being cold. Right? If it's something, if the distribution function were warm, means that in a given location you might have many different velocities for the dark matter particle. Right? So in this case of a cold fluid, you have only a very, very thin sheet in this space. Right? So if you go to 6 dimensions, 3 velocities and 3 positions, this dark matter sheet occupies a 3-dimensional manifold. right? So this this is a way of imagining it, the Vlasov equation, or the distribution function description of dark matter. Right, so what is going to happen now with evolution is that this distribution function starts wrapping into itself. Right, so this now is a 1+1 animation of the evolution of the phase space for a initially relatively cold fluid. So this was velocity, and this is position. So now, well, it's going to play again. So I want you to focus on see what is happening. Right. So we're going to start with something that's very smooth, means that there were no fluctuations, and then essentially the fluid goes up, has a lot of velocity, and goes down, means that the velocity goes to 0, and then starts wrapping it to itself, right? Yeah, yes? Right. So it's really telling you that this is a second order differential equation that has some essentially solutions, and if the distribution function along the solutions of that system has to be conserved, right? So it's essentially telling you this, right? That the number is the same if we assume that this movement happens using, well, in this case, Newton's law, right? Yes? Sorry? Right, yeah. So the question is that how do we guarantee that this property is fulfilled if we have not a continuous distribution function, but something made out of a finite number of particles? And the answer is that, well, you cannot guarantee, and actually I'm gonna go to that point in a bit. Right, so what is happening here, right? Now we see that the phase space is wrapping into itself. So now you can imagine that you have essentially, you can imagine two particles and start approaching each other, and then they become fast, they move faster and faster. That's why you have something going up and something going down, right? So they start accelerating and then they cross, and then they start deaccelerating, and then they fall in back and they start oscillating, right? So this is what we are seeing in this phase space, right? So now we start wrapping into itself, which is multiple. It's also known as shell crossing, right? Multiple crossings of this distribution function. So in the hands-on tutorial, we are going to try to code ourselves this particular example. Right? So this was a simple case in 1D. So now we can move to two dimensions and see how this picture starts explaining the cosmic web. So now we have this initially smooth distribution function that is going to start collapsing into itself and unfolding, right? So these folds happen here, and that is what is essentially leading to filaments, and then it collapses along the other axis, and this is now forms the dark matter halos and the knots in the cosmic web. Right. So, so in principle, we have somehow solved the problem, right? So it's we know the equations that we need to solve, and we need to solve them, right, with this Vlasov-Poisson equation. But unfortunately, it's very, very hard to solve that equation for anything but a set of very specific cases. So you need to resort to other type of methods, right? You cannot solve directly the Vlasov-Poisson. So and this is what leads to the n-body method and the numerical simulations, which make assumptions about how to solve the Vlasov-Poisson for this collisionless cold fluid. But before that, I mean, we go back to the Vlasov-Poisson and we can say, well, let's try to solve it. And a way that you can try to solve them is by taking moments of this equation. So velocity moments. So now you integrate the Vlasov-Poisson over all velocity space times velocity to some power, right? So the first power is 0. Actually, after some math, you can demonstrate that that leads to the continuity equation. So essentially, it's telling you the conservation of mass. So then, if you take u now u sub k as u, then you can derive this, and then you can show that you can arrive to an equation that tells you about the conservation of momentum, right? And then you can do that for u squared, and that is the energy equation, U cubed, U fourth, all the moments, right? So one interesting thing is that for a cold collisionless fluid, this hierarchy of equations is infinite, right? And then the nth order equation depends on n minus 1 cumulants of the distribution function, right? So essentially, this to solve this equation, you need to solve the previous equation. To solve this equation, you need the previous one, and so on. So it's a full hierarchy, right? So it's very, very hard to solve, right? Actually, it's particularly hard for collisionless fluids. So if you have a collisional fluid, like a gas or something like that, microphysical interactions lead to essentially you can have a Gaussian distribution of small-scale velocities. Right? So it's some sort of thermalization on small scales, and that closes the hierarchy. Because then you don't have all the higher order moments of the velocities are zero. But for dark matter, you cannot do that, and in principle it's infinite. So what do you do then? Right? So you typically assume two things. One is that there is no kurtosis. Essentially, you neglect all the higher order moments. Sorry, vorticity. You assume that any vorticity is zero. And also you assume that these velocities and overdensities are small. And then you can go and solve these equations. Yes? This is the velocity, well, there's different gradients of the force. It's essentially the tides that will create anisotropies on the velocity dispersion tensor. Right, so if you do this linearized solution of the blast of moments, you end up with linear perturbation theory. Right? So I believe you had lectures about that, and now you can go and solve these equations for dark matter, and we can see, for instance, the initial power spectrum of fluctuations. This tells you how much fluctuation there is on different scales in the universe. The amount of fluctuations grow in a way that is independent of scales, and all the physics is captured in the shape of these primordial modes. But unfortunately, you can see that even though this is a valid approximation at very early times, and actually this is what is used to solve in class or camp to predict the fluctuations in the CMB, when you go to nonlinear fields, as in the universe at low redshift, these assumptions fail, right? So you have to do something better. So it's actually an active field of research where you try to take higher order perturbation theories on different flavors of perturbation theory, but essentially it's solving the same type of equations, but trying to do more accurately. But unfortunately, there is, even though there has been progress over the last years, very quickly, as soon as you enter the nonlinear regime, all these solutions break, and then you have to resort to numerical solution of the equations. Right, and that leads to the n-body method, which is it can be thought of a Monte Carlo sampling of the distribution function, and then you solve the equation for this Monte Carlo sampling. Right. So let's go back to our phase space distribution. Right. So it was this sheet in 2D. So instead of solving for the full evolution of this distribution function, we just sample it at some points. You can choose them randomly or more homogeneous, and then solve for the equations that would govern the evolution of these points in phase space. Right? So actually, if you do this, then you end up with equations of motions that actually are the same as the equations of motions of the Hamiltonian of classical mechanics. Right? So now you can think that now each of these points is what we call a dark matter particle in a numerical simulation. It's not really is that a microphysical dark matter particle, but in a simulation it's just if you want a chunk of phase space that we assume that is just determined essentially by one point, and we are going to follow that, right? Right. So now the equations are simpler, just classical mechanics, and this is the equation we need to solve now, right? So this is the n-body equation, which just tells you that the acceleration that a particle feels is just 1 over r squared, like 1 over the distance squared to other particle, and sum over all particles, right? So this is essentially the equation known for 300 years now, and despite being very simple, right? It's just sum over 1 over r squared. It's quite hard to solve, right? And actually has many interesting properties, and because it becomes nonlinear very quickly. And nowadays it's very important in many areas of physics, astronomy, to explain the motions of planets or the globular clusters, the stars in galaxies, or the movements of galaxies in clusters. It's this equation that we have used to send rockets to the moon, and also we use it to explain the large-scale structure. Right, so it's a very interesting equation, actually, that the n equals 2, so the evolution of two particles evolving under the self forces was already solved in 1770 by Johann Bernoulli, and then you very quickly realize, actually Newton realized already when trying to explain the movements of planets, that it's very complex, because now, for instance, to explain the movement of the Earth around the Sun, you not only care about the mass of the Earth and the mass of the Sun, but you also need to account for the impact of every other planet, right? So actually, for many years, the solution was thought to be unsolvable, at least analytically. So actually, this is an interesting story that happened in 1888, when the king of Sweden and Norway, the Oscar II, set up a prize for his 60th birthday, I believe, that he was going to give, I don't know how much money, but I think roughly like 1 year's salary to anybody that could prove or could find a solution to this equation as a convergent series. Right? That was considered one of the most important problems at the time. And there were many people, the greatest mathematicians back then, they were trying to solve this problem. And actually the prize was won by Henri Poincaré by showing that actually there's no solution to that, right? And he was showing you that the small fluctuations will actually grow in time. And actually that was the birth of the chaos as a modern field, right? And he won the money for and the prize like then for solving that. But more recently, actually, was a solution for n equals 3 was found as a convergent power series. And actually, the full solution was done in 1991 by a PhD student in China. That now you can show that this is actually solved analytically, right? Well, you can track the problem analytically and solve it as a power series. But actually, I think it's a very interesting topic, because despite now this being, now you can say, well, now we have a solution to this problem. That does it mean that the problem is solved somehow? And the answer is no, right? So the reason is because all these solutions can be expressed as power series, but that involve millions of terms. So from any practical point of view, you cannot really solve them. So even though now we have a formal solution to the embody problem, we have not gained any better intuition or any practical use from this theoretical from this development. But instead, the Poincaré actually, by showing that or trying to solve and showing that there wasn't a solution, at least with the methods that were available to them back then, actually sparked a new field that now we consider much more important than finding the actual analytic solution to the embodied problem. Right, so right, summarizing this is that even though we know the solutions for these equations, we still have to resort to solve it numerically, right? At least in large-scale structure. Right, so the question is, how do we solve this second-order differential equation? And this is relatively simple. We can define this vector, that is x and v, and write this second-order differential equation as a system of first-order differential equations, right? This is a standard method. And now we can write this in a vectorial form, right? And then we use finite differences of version of this equation, which tells you that the solution of w at L plus 1 is w at L plus, it's a Taylor expansion, right? And that involves derivatives of this evolution term and powers of an interval delta t, right? So if you truncate this sum to first order, this is the very famous Euler method, right? And if you want to if you try to keep higher and higher order versions of this, it leads to all these families of Runge-Kutta, probably you're all aware, Runge-Kutta 4, 5, and so on, are nothing but keeping higher order terms of this equation. Right? So in principle, you can say, well, we need to solve the embodied problem. We just need to go and use one of these forward Euler on Runge-Kutta. But actually, there is a even better way of solving this, which is instead of evaluating the derivatives at L, we can use that we can estimate the derivatives of L plus 1/2. So it's like the mid-rule method for integrating functions. And that in numerical cosmology, that's known as the leapfrog scheme. Right? So the idea is that instead of taking the evolution at, you said at the same point in time, we use it, we put velocities and position at different times, like they're interleaved by time step over half, right? So we have a position that's also known as drift operation, and then we estimate the velocities and the accelerations that we evolved to this point. Then we use this state to compute the forces, and then we use that to evolve the velocities, and then use these velocities to evolve this particle, and then use these particles to compute forces and evolve it here and so on, right? So it's a kick and drift operators also, right? So it's quite interesting this leapfrog scheme, because it's, despite being a first order solution, has a second order accuracy, means that actually behaves better than or it has the simplicity of a forward Euler, but much better convergence properties. And it has other advantages that are quite desirable when solving for these systems. One of them is that it's time reversible. You can see this very easily, that you take one point, you can evolve forward up to this, and then change the sign of the time, and then you're going to end up exactly at this point, right? These are time reversible as the underlying equations of gravity are. So this is a property that you would like to have. Then also conserves angular momentum exactly in spherically symmetric potentials. And also has a very important property, which technically is called symplectic. But what means is that it preserves the volume of phase in phase space. And this is also a property that the underlying, essentially Liouville's theorems, it's a more technical term, but this is also some property that the underlying equations of motions have. And this is, right, so you can imagine why this is a good idea if you take two particles that are very nearby in orbital space, and then you evolve them. So the fact that this is conserved phase space volume means that the orbits cannot be too different after some time, right? They have to be kind of bound. This is very different to Euler or the other integrations that actually the orbits can diverge. And actually you can see that for instance, energy and momentum is conserved much better when you use these symplectic integrators. So actually in a more technical note, you can actually demonstrate that all the other time integrators, the forward Euler and Runge-Kutta of any order, actually are the symplectic solutions to a nearby Hamiltonian. So you can assume a different Hamiltonian that is the original Hamiltonian plus some function of delta t of the interval, and the symplectic solution of this is like the symplectic solution to H prime is like the non-symplectic solution of H plus some function of H of the time step. Okay, so right, so now we know how to integrate our equations of motions, but we have another problem in numerical simulations. That is that we have very different timescales, right? Sometimes you have a very massive dark matter halo where the orbital timescales are very, very short. So you would like to have very short time steps, but in other regions like a huge void, movements are linear and nothing much happens. So then you could afford having longer time steps, right? So for that, it's customary to use adaptive time steps. For instance, one that depends inversely on the acceleration, and then you can rewrite your time stepping scheme to account for these adaptive time steps, right? So you can have, in this case, for instance, what is called a kick-drift-kick scheme, which is that you have a half step at the beginning and a half step at the end. So here you update the velocities only by delta t over 2. Then you have a full drift operation, and then you have another half kick at the end of the step, right? And then you can go here, and then you can change your delta t to something that is better suitable for your particular moment in time and particles. So this is actually quite good. It's a very, very useful thing to do. But the price you have to pay is that you don't have time reversibility anymore, right? And actually, you as far as I know, there is no symplectic integrator that can be used with adaptive time steps. Right, so another, though this is pretty standard. So one problem that people start encountering recently in the last couple of years is that to understand errors, to understand uncertainty in data or so on, you need to generate many, many thousands even of numerical simulations. So for them, you had very long time steps to make them faster. So then terms that we neglected, all these delta t cube terms that before we didn't even mention, now become important. And actually, then they lead to noticeable differences in the power spectrum and all properties. So there have been two suggestions for how to modify these time integrations to ameliorate for this problem. One is it's called COLA, co-moving Lagrangian acceleration, where the idea is to combine this time integration with perturbation theory. So you subtract to the velocities the contribution that you would expect from perturbation theory, and then you add to the position the contribution that you expect from perturbation theory, right? So it's like solving for the equations of motions around the perturbative solution. And another method is called FastPM, in which essentially you assume, in this case, we are assuming that the acceleration is constant in time. This method, you assume that it's not constant, but actually that evolves according to linear theory, for instance. So instead of being acceleration that's given by the potential, goes like the growth factor times the potential. And that has been, I think, quite useful recently. So, right, so we know how to integrate our equations of our n-body equation. So the only thing remaining is how to compute forces. And so this is the same equation. You imagine you have a bunch of particles. Now you need to compute the acceleration for a given particle is the sum over all particles of essentially 1 over r squared, right? But you need to do this for every particle. So this is a n squared problem that for a small number of particles you can do, but very quickly becomes really, really hard to do. So there are different ways or alternative ways of computing forces. One of them is to write down the Poisson equation on a grid and solve them using Fourier methods. This is called particle mesh. So now you can imagine you have a bunch of particles, and now you have a grid, and then you estimate density field by depositing the particles on your grid. You have different first, second order ways of doing this deposit, but well, it's just a detail. And now once you know that the amount of particles in each cell, you can estimate the density field, and then from the density field, you can solve the Poisson equation. You have the Poisson equation, and you can go to Fourier space, and the Laplacian becomes 1 over k squared. So you can estimate the Fourier transform of the potential, and then you know the acceleration is the gradients of the potential. That in Fourier space is a multiplication by k, and then you can combine this with the estimation of the potential to estimate accelerations based on essentially multiplications in Fourier space. So that's actually very, very useful. There are many libraries that compute these Fourier transforms in a very efficient way. You can use them in large supercomputers, but it has problems, right? That you are limited by the spatial resolution of your grid, right? The force, the estimation of the acceleration has the spatial resolution given by your grid cells, right? So this imposes a limit that you would like to have better resolution to resolve what internal destruction of halos and other things. So one alternative is to use to start refining the mesh and then having, for instance, more cells in regions of interest, and that's sometimes used. Or another way is to change completely the method And instead of doing the deposit, we can do what's called a multiple expansion of the forces. So the basic idea is that if you have a bunch of particles far from you, instead of summing over all of them, you can consider them as one single massive particle, and then you just sum the force, the contribution of that big particle, right? So more formally, what we can do is an expansion of the force in terms of moments, and then we compute, only the monopole or quadrupole and so on. Typically now in modern codes, you stay with the monopole, but if you want higher force accuracy, you can include higher order terms in your force. Right, so this is quite useful because now when you have particles, especially when particles are very, very clustered, right? So if you have a lot of particles that are always very close together in groups, right? You can always approximate this very well as a massive particle and becomes very efficient. Right? It also has advantage that you can have now individual steps. For the PM, for the particle mesh, you always have to have a single global step because that's the calculation, essentially the calculation of the force involves all the particles and it gives you acceleration everywhere. Right? In this case, you can compute the force only for the places that you're interested in. Right? It has other problems that, for instance, when you have a very smooth mass distribution, now you rely on a very accurate cancellation of forces. Now all the particles over there have to cancel the force of all the particles on the other side, and if the cancellation is not quite correct, then you can have artificial accelerations. So a solution for that is very common is to split the force calculation into two parts, one that involves the long range forces and the other involves the short range. And the long-range forces are given by the particle mesh, and the interaction with particles nearby involves or are computed with the tree method. Okay, so you have 8 minutes, right? Huh? How much? 15 minutes. Okay. Right. So now we know how to compute the forces. We know how to integrate them in time. There's one actually probably one of the most serious problems on numerical simulations, which is that you can see very easily from here that when two particles become very close to each other, this distance goes to 0 and the force diverges, right? Goes to infinity, right? So we need a regularization parameter. That regularization parameter is usually referred to as the softening length. And now you have a modified embodied equation that is not only 1 over distance, but it's the distance plus some parameter, right? So now the forces are don't grow without bound, but they have an upper limit that depends on the value of this softening. So it's a parameter that you actually need, but also has some drawbacks, right? So you have now systems that, well, actually I'm gonna switch here. So now you have a parameter that will introduce some effects, and now you have them, and it's not obvious. Actually, there's a lot of debate in the field as to how to choose this softening length, right? So you have several considerations. On one hand, you would like it to be larger than the mean interparticle separation. You can imagine that the softening length, if you have two particles, we are actually trying to describe, if you remember from the beginning, a full continuous distribution function. Now, it happens that we didn't have enough resolution to sample things in between, so only we sample these 2 points. So from that argument, you can imagine that the softening should correspond to the typical size of the chunk in phase space that you are trying to simulate, right? So this means that typically the softening should go like the volume over the number of particles, cubic root. But even though that is true for your initial field, when you are evolving, this probably means that what you care about is the mean interparticle separation at a given time in Euclidean coordinates, right? At redshift 0, not how it was at the initial redshift. So it's not clear when one should apply this. And actually, one line of research is the development of adaptive softenings, which essentially try to apply this condition, but on a position-dependent manner and a time-dependent manner. Right. So another thing is that you would like it to be smaller than the smallest object that you're going to try to that you're going to simulate in your experiment, right? So if you're going to resolve objects with 100 particles, for instance, you would not want the softening to be larger than the typical size of these 100 particles, right? So this mathematically you can write this on this expression, and that it corresponds to roughly about 3% of the mean interparticle separations. But also you would have other conditions. For instance, now you have a discrete system. Imagine you have 100 particles, and now you also would like that the binding energy between the two particles due to this gravitational softening to be less than the binding energy of the whole halo, the whole structure that you're in. That puts another limit that is actually not so different to this one. And another way, another argument that you can make is that the largest acceleration that you would like to have in your system, due to the essentially the softening, to be smaller than the mean acceleration that your particles would feel due to the rest of the particles, right? So that the acceleration of the two particles would be smaller than the mean intra-halo acceleration. Right, so this puts several constraints, and this is what is summarized here in a paper by Aaron Ludlow. What is the softening as a function of mass of the halo that you're considering? So here you have these different limits that I was talking about. If you consider the acceleration criteria or the binding energy one, and so on. Right? So this is the kind of the minimum one that the region that would not be allowed, right? But then you realize actually that even though the softening is a very important parameter, usually numerical simulations are not limited by the softening, but by two-body relaxation timescales. Like typically in a collisional system, or when you have a finite number of particles, you will have still many two-body or scattering events. Yes, a question? Sorry, can you repeat? What would happen if the softening is smaller than the mean interparticle separation? Actually, I think almost all simulations that have ever been, 99% of the simulations that have ever been run have softening lengths much smaller than the mean interparticle separation. So I mean, to be honest, I don't think anybody really knows how the discretization, this error propagates in the results. You just try to do convergence studies, solving the same problem, varying the softening length, varying the number of parameters, and try to determine a convergence radius. But I don't think there is a proof that you get the right result on a scale smaller than the mean interparticle separation. Yeah. Actually, there are people that would seriously advocate that you get the wrong result on a scale smaller than the mean interparticle separation. Yeah. So, right. So these are the different considerations that you have to have when you run the numerical simulation. Choosing the softening is very important, but typically your results will be dominated by two-body relaxation timescales that determines the minimum scale in which the relaxation timescales is roughly of the order of the Hubble time. Okay, so we know we know how to write what is the embodied equation we need to write with the right value of the softening. We know how to solve this equation dynamically. So the only thing that is missing is what our initial conditions are, where we start. So the problem is that we need to create a field that is compatible with the statistical properties that we see in the CMB. That is, for instance, in a case that is a Gaussian random field, means that the real and the imaginary part of a given field are Gaussian deviates with zero mean and a variance given by a given power spectrum. In Fourier space, that means that the amplitudes are distributed by this form, it's a Rayleigh distribution, and the phases, if you write this in a polar form, are uniform between 0 and 2 pi. Right, so now we know what the density field should be like, so we can create them, and then and we just divide k squared, and then we know the potential of this field. Right. So one thing is, because the Gaussian field is, we are not simulating the universe, right? We are simulating a universe that is statistically compatible with what we see. But we can choose many of these universes, right? So this is showing you all different random fields that all have exactly the same power spectrum, but there are different realizations of the phase field. You can see that it's very different, and that is what leads to what's known cosmic variance in the simulations. We are just simulating a given region of the universe, and we compare it to the real universe. Sometimes we might be unlucky and simulating a huge cluster or a void or something like that. Another field of research is to try to estimate that from the observations of the local universe what this field actually is, by trying to go back in time. Okay, so then, so now that we know what the potential is, we can actually use the results of perturbation theory I was talking to you about earlier to estimate what the initial positions and velocity of the particles are. Right, so now we can write the continuity equation. Okay. 5 minutes? Okay, thanks. Right, so we can use this linear order perturbation theory to estimate what the initial positions and velocities of our particles are. And this is, if you keep your equations at linear order, that is called the Seldovich approximation. It just tells you that the velocities are just proportional to the gradients of the potentials and the positions also. So these are particles that actually is going to start moving on straight lines. So now we can, this is actually a realization of particles that I started moving using the Seldovich approximation. Right? Now you can see that initially they were very homogeneous, and they start moving, and first you can see, focus on a given particle, it always moves on a straight line. If you have shorter versions of particles, they actually would have some curvature, but not in this case. And then you already can start seeing also that some structures form. And it's actually very useful already from the Seldovich approximation to analyze the structure of the solutions, and then you realize the different type of structure that can happen, right? So if you write what the density is, in one case was, well, it actually can be written as the Jacobian of the transformation between your initial smooth particles and the one predicted by the Seldovich approximation. This is a matrix that you can then diagonalize and take eigenvalues, and this density at the end can be expressed as 1 over 1 plus some eigenvalues. So you can see here that there are essentially some points, if the eigenvalues are negative and D is the growth factor, start growing, there is a point in which each of these terms will be 0, and means the densities would be infinite. Right? This is known as shell crossing. Right? So if you have one of them being zero, you can have a sheet, and then 2 of them a filament, and the 3 of them is a halo. Right? So these are the same. So what does it mean that this actually goes to 0? It means that the Jacobian essentially means that 2 particles that were initially in the same place end up, 2 particles that were initially in different places end up on the same place. Right, so this mapping is singular, and then is what this happens, right? Okay, so I think I'll skip this. Right, so I think we have our embody code by now. We can compute the initial conditions using the Seldovich approximation, from which we create first a Gaussian field with properties compatible with the CMB. Then we are going to loop over a number of time steps with a leapfrog symplectic integrator. So we make sure we conserve phase space and energy and so on. So first we kick velocities by half step. We drift the particles, we advance them, and then we compute forces using a PM, a tree, or a combination of them, or a full embody with a properly chosen softening length. And then we can kick the velocities again. And then because then we can estimate a new time step, and then we loop over this, right? And this is actually what we are getting with this integrator. So initially it was very smooth, and now we are forming all the filamentary structures that we saw in initial moving. If you do something fancier visualization of the same particle distribution, you end up with something like this. I'm not sure you can see well, but this is actually one of modern embodied simulations. Should I stop or okay? Right. So well, so how long do I have now? A few minutes. Yeah, maybe. Right, so I will give you a hint on, or maybe I will explain this a bit better next lecture. I wanted to finish with this thing that now we've made emphasis on what are the underlying equations were and how we're solving them, and I think I try to make an emphasis that we're doing a numerical solution of a set of physically sound equations. So as with any other physical system or numerical solution to a physical system, they're not perfect, right? We have numerical errors, but these numerical errors are controlled by various parameters. We mentioned softening length, with the step size, and so on. So when you try to solve or try to simulate the universe, it's very important to keep in mind that numerical simulations are not exact, but they have various parameters associated to them, and actually this is currently a very important field of research now, that to understand what are the errors associated with numerical simulations and how we can keep them under control. So I think I will stop here. I will continue from this point tomorrow. No, thank you. Any questions? Right. So the question is whether we see that small galaxies merge to form big elliptical galaxies, right? So yes, actually that's another active field of research to see what happens really during mergers. And yeah, in general, what happens is that you have these galaxies that are spiral, where all the gas and stars settle on a disk, but then you have mergers. And that actually, there are several processes involved in the mergers, but in particular, I think violent relaxation is one of the most important ones that tend to open a larger space of energies, and then that leads to more orbits that can be supported, and that end up roughly in a bigger, more elliptical galaxy. You destroy the disk. Actually, destroying disks is relatively easy to do in simulations. Any perturbation actually would destroy the disk and form more spheroidal type looking galaxies.